So welcome to the first error correction session of QIP. First up, we have Kewen Wu from Berkeley. He'll be talking about quantum state preparation with optimal T-counts.
Okay. Is my voice clear? Okay. Yeah, I'm Kewen Wu from UC Berkeley. This is a joint work with David Gosset and Robin Kothari. I will be talking about quantum state preparation with optimal T-count. All right, since I'm the first, I get the privilege to tell you what are Clifford gates. Okay, Clifford gates are introduced for quantum error correction, but it has other uses. In particular, it's just 3 gates. We have single qubit Hadamard gate, single qubit phase gate, and 2 qubit control NOT gate. And just by having these 3 gates, we can already generate something non-trivial just for quantum. For example, for the first one, we can witness entanglement by creating Bell state. And for the second, we can do this Fourier transform over discrete hypercube that is just 1 layer of Hadamard, but the classical computation needs n log n time. So given these Clifford gates, the Clifford circuit is just a circuit consisting of those Clifford gates. And because it witnessed so many interesting quantum phenomena, we wonder whether this is all the gates we need. And apparently, it is no. For universality, just with Clifford gates, it cannot generate all the quantum computation you want. And also, for Gauss-Mann-Canel theorem, we know that if your circuit only has Clifford gates, then you can do classical simulation. The runtime is polynomial in n. In other words, you don't need quantum computer. So how do we fix this? Well, it turns out it's not too hard. We just need to include another single qubit gate called the T gate, that is the square root of the phase. And by introducing this gate together with the Clifford gates, it becomes a complete set. So these gates will be able to represent all the quantum computation. And also, for this, we have a generalized Gauss-Mann-Canel theorem, which says if you have a Clifford plus T circuit, then the classical simulation runtime is polynomial in the circuit size and exponential in the number of gates, in the number of T gates. So this is like a generalized version of the Gauss-Mann-Canel theorem that I presented 1 slide ago. Okay. In the study of Clifford plus T circuit, a general goal is to reduce T count. That is the number of T gates in the circuit. Well, this comes with 3 motivations. The first one is regarding classical simulation, that is the Gauss-Mann-Canel theorem that I've just mentioned, meaning that if you have a quantum circuit that consists only of Clifford plus T gates, and you have few number of T gates, then you can run this Gauss-Mann-Canel algorithm, and the runtime will be pretty fast in classical machine. So this is pretty good if you don't have quantum computer. And secondly, in the physical implementation, the fault-tolerant implementation of T gates is more expensive than Clifford gates. Although in the next talk, I suppose Craig is going to subvert this claim, but let's stick to this for now and leave questions for him. Okay, the third one comes from magic. That is, we want to understand how much non-Cliffordness is needed for various tasks. Because as you can see by Gauss-Mann-Canel theorem, if you don't have non-Clifford gates, then it's purely classical. So people want to understand how much non-Cliffordness you need, aka magic. And there is a whole workshop last year working on quantum magic. So yeah, these are the motivations. And let me give you the task we focus on, that is state preparation. In particular, we care about the following setup. For n-qubit quantum states, we want to construct it in a Clifford plus T circuit with minimum number of T gates while making sure we prepare the state in epsilon error, that is in L2 distance. And this is a fundamental task in various quantum algorithms, communication, metrology, and experiments. And let me be more precise here. So here we have a bunch of wires, circuit wires. And the first n are blue wires, and they are initialized at 0. And the rest are additional workspace, ancillary qubits. Those are the red lines. And they are also initialized as all zeros. And then you can put some Clifford plus T circuits on top of it. That is, you have this hard mod, phase, C0, and the T gate. And as you can see, I highlighted those T gates. So those are the costs we care about. And in the end, we want to produce a target state on the first n wires within epsilon arrow. And we also want our algorithm to restore the ancillary qubits to be all zeros for later use. So this is the setup of our algorithm. And given the setup, let me tell you about results. Okay, let me focus on the single qubit case. That is, for single qubit quantum states, how many T gates do we need to construct it within epsilon arrow? And for this, you can apply a sort of Kitov theorem, and you will get some poly log 1 over epsilon bound. And this poly is like 3.97. And by a beautiful line of work, they use algebraic number theory, they were able to bring down the upper bound to log, a single log. So you only need order of log 1 or epsilon many T gates to prepare any single qubit quantum state within epsilon arrow. And this turns out to be optimal. Like there are states that needs this amount. So the picture is fairly clear for the single qubit case. And let me move to the general case. So imagine you have some n qubit quantum state and you want to implement with minimum number of T gates. And let's say you just want 0.001 error. So it's a constant error. And you can do this by some natural attempt. Let's say we start with 2 to the n many single qubit gates with two qubit C0 gates. And then we will approximate each single qubit gate with, to this inverse exponential error. And then by union bound, the total error will be constant. And by doing so, you will find that the number of T gates you need will be 2 to the n times n. Here, the 2 to the n is the number of single qubit gates you initially used, and the second multiplicative factor n comes from the single qubit approximation by converting it to Clifford plus T. So this is the folklore results, and surprisingly, by Low, Kliuch-Nikolov, and Schaffer, they show that you can shave a square root factor, meaning that you don't need 2 to the n times n T gates. You only need to use square root 2 to the n times n log n many T gates. And they also prove a corresponding lower bound that is square root 2 to the n. And in this regime, our contribution is to improve the upper bound. We show that you can shave those n log n factors. And this is asymptotically tight considering their lower bounds. So for the constant error case, both the upper bound and the lower bound are square root 2 to the n. Okay. So what about the general case? Let's say we have n qubit quantum states, and we want to construct it within epsilon arrow. And then in their paper, they also have a bound that's like square root 2 to the n times n log n over epsilon plus an additive log square n over epsilon. And they also prove a lower bound that is square root 2 to the n log 1 epsilon. And also, if you put n equals 1 there, the lower bound is only square root log 1 over epsilon. That is inferior to the single qubit lower bound that I mentioned, which is log 1 over epsilon. So we really need to kind of combine the two lower bounds we know here. So even though the first thing has a giant 2 to the n in it, but for small constant n, it's worse than the single qubit lower bounds. So this is prior works. And our contribution is also bring down the upper bound to match the lower bound. So our upper bound is square root 2 to the n log 1 epsilon plus an additive log 1 epsilon. And as you can see from the two lower bounds, it is also necessary. Okay. So along the way, we also get some interesting byproducts. I think maybe you will find interesting as well. So this is regarding unitary synthesis. In particular, we can we analyzed the T count for generating diagonal unitaries. So given all all kinds of n-qubit diagonal unitaries, how many T-gates do we need to construct it within epsilon error, let's say in spectral distance. And this appears in prior works as a key component for state preparation. And there are some other interesting applications that I'm going to show you. And perhaps not surprisingly, this bound is the same as the state preparation, because you can intuitively view that diagonal unitary is putting the state on the diagonal. So they have the same degree of freedom, and you expect the same T count. Okay, what is the application? The first application is called batched synthesis, where we want to prepare a bunch of different single qubit unitaries. So let's say we have U1, U2, U3 up to UM. These are the M single qubit unitaries, and we want to implement them all. What is the T count for it? There is a natural attempt just to implement them individually, and then union bound the error. So so the individual error will be epsilon over m, because there are m of them. And then the total T count, if you calculate it, will be m times log m over epsilon. So here, this first m, because you have m UIs, and the additional log of m over epsilon comes from the fact that you need to use single qubit unitary synthesis results. And from our work, we show that if m is at most roughly log 1 over epsilon, then the cost doesn't blow up, meaning that you only need to use log 1 over epsilon many T-gates to prepare log 1 over epsilon many different single qubit unitaries. And as I mentioned, this budget cost, log 1 over epsilon, is necessary even for m equals 1. So this is really the unit cost. And also here, if you plug in m equals log into the natural attempt, you will find the bound to be log times log. So we indeed saved something. And the proof is actually simple that I can show you in one slide. So my goal is to show that U1 tensor U2 tensor up to UM is order log 1 over epsilon for m equals log 1 over epsilon. So that is the circuit that I'm trying to prepare. And the first step I'm going to do is to diagonalize it. By standard tool, for example, like Euler-Angle theorem, we can decompose any single qubit unitary into the product of Hadamard and the single qubit diagonal unitary. So each uj equals aj times h times bj times h times cj. So h is a Hadamard, a, b, c are diagonal. So in other words, the one layer circuit now becomes 5 layers. You have a, b, c, and h among them. And because Hadamard is already Clifford, we just focus on those A's and B's and C's. And let's say, for example, for C's, C1 tensor C2 tensor up to Cm is a tensor product of single qubit unitaries that are diagonal, meaning that itself is a diagonal unitary, although it's on m qubits, right? Because you are tensor product of diagonal, you get diagonal. And as I mentioned, we know the T count for diagonal unitary, which is square root 2 to the m log 1 epsilon plus additive log 1 epsilon. So then you just plug in m equals log inside, you get square root of log times log, that's a log. So the total cost is only log 1 epsilon. So it's a fairly straightforward proof. Okay, so this is implementing different single qubit unitaries, and we get some log saving. And you may wonder, what about the case when they are the same? Like, I want to implement many single qubit unitaries that are the same. And this is called mass production. And indeed, we saved more than log. So let U be a single qubit unitary, and we want to implement U tensor M. So here it's like M copy of the same thing. And we want to understand the T count. And for this setting, we prove that the T count is asymptotically m plus log 1 epsilon. So this is upper bound, and also the lower bound is, we also prove lower bound. here, the log 1 epsilon is necessary even for m equals 1. And this linear in m factor is necessary also because if your unit array is T-gate itself, then you cannot hope to generically compress T-gates. So this linear factor is also necessary. And if you compare with what I showed you previously, with the fixed budget of log 1 epsilon many T-gates that is necessary even to implement one single qubit unit array, we can use batch synthesis to implement log 1 epsilon many different single qubit unit array, or we can use this mass production result to implement log 1 epsilon many same single qubit unit arrays. So this is our saving. Okay, let me briefly summarize here and mention some open problem. So for state preparation and diagonal unitary synthesis, we obtained optimal T count that is of that form. And we also provide two interesting applications to save T-gates in implementing a layer of single qubit unit arrays. In particular, if they are different, you can use batch synthesis. If they are the same, you can use mass production results. Okay. Now let me talk about open problem. The first one is regarding this batch synthesis. So as I mentioned, if you only want to implement log 1 epsilon many different single qubit unit arrays, you can do it with T count log 1 epsilon. And this log 1 epsilon is necessary because even for a single one you need, but I didn't say that the log is the best you can do. So it is possible that you can use log 1 epsilon many T-gates to implement log 1 epsilon many different single qubit unit arrays. And we don't know how to make this work or rule this out. So this is an open problem for you. And the second open problem is regarding unit arrays. It's kind of natural that we can analyze the T count for state preparation, and you can ask, okay, what if I want to prepare a general unit array? How many T-gates do I need? To do this, you can actually do it by reducing it to state preparation. This is because any n-qubit unit array can be decomposed into product of 2 to the n many reflections. And each reflection, okay. And each reflection is I minus this 2 bracket psi, and it's essentially preparing this, this state psi. And then, because I have told you that the state preparation T count is roughly square root 2 to the n, and here I'm even like ignoring the dependence on epsilon, and lower the terms in terms of n. And by plugging in this result into this decomposition of reflection unitaries, it will give you this this bound. So for any arbitrary n-qubit unitary, you can prepare it with T-gate roughly 2 to the 1.5 n. This is because you have 2 to the n many reflections, and each one needs square root 2 to the n. So in total, it's 2 to the 1.5 n. However, we can only prove lower bound that is 2 to the n. So this leaves a polynomial gap, even in terms of 2 to the n. So the lower bound is 2 to the n, and the upper bound is 2 to the 1.5 n. And the question here is, can we bring down the upper bound? Is it possible to implement arbitrary unitary in Clifford plus T circuit with only 2 to the n T gates? And the reason why we hope so is because we want a similar square root saving as we see in the state case. So a quantum state has like 2 to the n degree of freedom, but in the end you only need square root 2 to the n many T gates. And here the unitary has like 4 to the n many degree of freedom, and we would like to see a square root saving instead of this like 2/3 saving. Okay. In the end, let me just mention some buzzwords for the proofs, how we actually did this unitary, diagonal unitary synthesis, and how we constructed states using Clifford plus T circuit. So the first is for diagonal unitary synthesis, we actually rely on very old wisdom to implement Boolean oracles. So this is some results in Boolean circuit complexity that dates back to 1960s to implement Boolean function using XOR gates and AND gates. And they use few number of AND gates. And then when you convert it into Clifford plus T circuit, XOR becomes C0 that we don't care, and AND become T gates that we care about. So this is very very old results. And we also rely on the single qubit unitary synthesis result to handle rotation angles, because we don't have we are not necessarily given Boolean diagonal unitary. We actually have like arbitrary complex numbers. So we need some way to handle like those angles. And this we use single qubit unitary synthesis results. And for state preparation, we actually have a very different algorithm. We will start with a constant approximation of the states, and then try to boost this constant approximation to epsilon approximation. And to do this boosting, we use this linear combination of unitary technique, and we also need amplitude amplification. And this algorithm is fairly similar to what Greg Bosenso was proposed for his unitary synthesis and state synthesis paper. Yes, this is all my talk, and thanks.
Okay, thank you, Kevin, for a nice talk. We have a bit of time for questions. So are there any questions from the floor?
Suppose you have a catalog of several non-Clifford gates. T gate, maybe TOEFL, maybe something else. Will it help in these kind of estimates?
I think maybe you can just first convert other gates into Clifford plus T, and this only creates a constant blow up. So asymptotically, I think that should be the same. But if you care about the constant, that certainly will help, yes.
Yeah, thanks for the nice talk and also very interesting paper. I got one quick question about the state preparation. And I was wondering, like, have you thought about, suppose when we consider the state preparation problem, but there's some structure in the coefficients of the state. For example, if we're doing scientific computing, and those coefficients can be some real coefficient from quantum chemistry calculation, maybe there's, say, major product state structure, or maybe it's like essential decay. And is there any room for further improving the current algorithm? The reason I ask this is I look into the first work you mentioned, and I think in the special regime, like the major product state structure or the when the coefficient has exponential decay or some other structure, actually the complexity match. So I was wondering for the current state preparation method, if we consider some special structure, will there be any room for the improvement?
Yeah, that's a very nice question, and I would anticipate there are some like savings when you go to special structures. When you, let's say, the state has some granularity guarantee or has some algebraic form, and we did look into some when we were trying to improve this batch synthesis case, and. Yeah, so yes, the short answer is yes. There are some cases where you can save something, and I think it will be a case analysis, like depending on your problem.
Okay, I think we should go on to the next talk now.
Sure.
So let's thank the speaker again.
Thank you.